All right, this is video 9 to the baby real analysis series. And in this video, we are starting a new topic and the topic is sequences. So sequences play a big role in analysis, and we will be spending special care with sequences, and we'll have multiple videos, several videos covering sequences. So this video is meant as an introduction. And as an introduction, let's say I had the following, and a sequence is basically a list of numbers. At least that's what I like to think of them as. And let's say I consider the following 3 lists of numbers. The first list, and I'll use parentheses to encompass my sequence. And I have it as 1, 2, 3, ... So our sequence is the natural numbers. Now AN, when you see it as that is called the nth term of the sequence. It's called the general term. And so when we have 1, 2, 3, a general term format would be n, where n's a natural number. So the nth term is just n. And this goes on forever. All right, so sequence, list of numbers, goes on forever. I use parentheses to encompass the sequence. Don't confuse a sequence with a set. So that is an important distinction. Now, for a set, I use the curly brackets, the curly braces for the set. And then for the sequence, I'm just going to use parentheses. And let me go back to these 3 sequences. The second sequence is 1, 1/2, 1/3, and the next one would be 1/4, 1/5, ... So it's got a general format of 1 over n, where n is a natural number. So the nth term is 1 over n. The third sequence it just alternates from 2 to 0. So 2, 0, 2, 0, and keeps going on forever. Now notice I have 2 for an odd term. So this is the first term is odd, or 2. And then the third term is 2. And then we have the second term, the even number is 0. The fourth term is 0. And so it keeps alternating like that. So every odd term it's 2, and every even term it's 0. So that's how I can say this in general format, or general term, the nth term. It's either going to be 2 or 0. It's 2 if n is 2k plus 1, where k is an integer. That just means it's or odd. And then 2 times k, or k is an integer, that's going to be even. So it's odd. So it's 2 when the term is odd numbered. It's 0 when the term is an even number term. All right, so there's these 3 sequences, and then I said don't confuse a sequence for a set. And the sequence example with 2, 0, 2, 0, where it alternates, is a perfect example. So it keeps going on forever. Now the only elements, the only possibilities are 2 and 0. So as a set, it would just be 0, 2, like that, where you only list any repeated items once in a set. Whereas in a sequence, you can have repeating items or repeating values. Okay, so these 3 examples we'll focus on in this, we'll mainly focus on the second 2 in this video. Now, for a sequence, you can think of a sequence as a function from the natural numbers to the real numbers, where the index for each term is a natural number. So 1 gets mapped to A1, 2 gets mapped to A2, and so forth, where n gets mapped to an, the nth term. So that means the one after that's the n plus 1 value gets mapped to the n plus 1 term. And then in general, you write it as parentheses an as a general format for the nth term, and then that equals a1 comma a2 comma a3 dot 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 goes on forever. And our example for the 1 over n, where it's 1 comma 1/2 comma 1/3, if we list it out, you'll see that it's decreasing and the values are decreasing, and it actually goes to 0. So this sequence converges to 0 as the indices get larger. As the indices get infinitely large. All right, that's what the as n goes to infinity. The sequence where you have just the natural numbers 1, 2, 3, 4, and so forth, that's getting infinitely larger. And so it's going to positive infinity as the terms get, or the indices get infinitely large. And then the sequence where it alternates 2, 0, 2, 0, this does not converge. So the question is, what would that converge to? It might be a reasonable guess. You might say 2, maybe 0, but we'll show that it does not converge to 2 or 0. Okay, so for what we mean by convergence of a sequence, we need to make it formal here. And that's where I have in or gold the definition of a sequence converging. So if the terms of a sequence an converges to some value a, that's a real number, as the indices get infinitely large, then the sequence an converges to a. Now in gold, the definition, and I wrote this in shorthand notation, but it says if the sequence an converges to a as a real number, as n goes to infinity, that means if and only if, for all real numbers epsilon greater than 0, there exists a capital N that's in the natural numbers, such that for all little n bigger than capital N, we have the absolute value of an minus a is less than epsilon. All right, so there's a little bit here to dissect. If I list the terms out, like A1, A2, A3, dot, 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 and then I get to A, and then it's got capital N. Now, that's a subscript, so that's my index, term with index capital N. And then after that, I have terms that have A, and then N plus 1, N plus 2, and they're all capital N's. Now, all of these values, all of these terms that to the right of AN, these are all the terms with indices in little n bigger than capital N. So when we're considering for all n bigger than capital N, we're really considering all of these values, all of these terms for that. And I think of it as a cutoff point. So the term with index capital N, I would think of that as my cutoff point to where you get to the limit, or yeah, to where you get to the limit. Okay, so graphically, what's going on here? So think of the x-axis as the natural numbers in, and they go like 1, 2, 3, dot, 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 and then let's up to n, and then n plus 1, and then n plus 2, and so forth. Now my y-axis, think of that as the values for the ANs. So what the actual values of the sequence are. And let's say right here, this is A1, and then it jumps to here's A2. And then let's say just it does some crazy stuff. Let's say it jumps to here's A3. And then slowly, say that's A4, and then let's make this a little bit better. Let's say that's AN, and then we have AN plus 1. And then AN plus 2, and then it just keeps going like that. Now there's some value, so what we're thinking for the limit of this, let's say the limit we're saying is A, so that's what the limit is. And there's some term in which we can find that the index for that term puts us within some confidence level around the limit. And that confidence level around the limit, we can narrow it down to being, let's see, so let's say these are our bounds to the confidence level, our confidence interval. And for that, we have some epsilon value. So we go A plus epsilon and then A minus epsilon. And then there hits a cutoff point, and that cutoff point, so for all values bigger than n, we're dealing with all of the indices like AN plus 1, AN plus 2, and so forth. So this is the term with index n. And then all of these terms have index bigger than n. And then all of these terms put you within the bounds. That is I'm calling our confidence interval, where we get to the limit A. Okay, so all of these terms are within epsilon distance from A. That's what that's saying. So all of these terms, I'm going to say lies within our confidence region. And our confidence region is the bounds are A minus epsilon, A plus epsilon. And that means each of these terms lies within epsilon distance from our limit A. All right, so we won't actually be graphing these, but I figured that might help. So think of it as a sequence. Your x-axis is like the natural numbers. Those are the indices for the terms. Your y-axis are the actual values. So those are the terms a, n. And then a sequence would be like these different dots jumping, doing some crazy stuff. And then eventually there comes a point where the terms get so close enough to where they are within an epsilon distance of this limit a. And you want to find, well, where is that point in which that happens? So you find index capital N corresponding to the term an, and then all of the values to the right of n, which is n plus 1, n plus 2, these are my values n that are bigger than capital N. Corresponding to the terms like an plus 1, an plus 2, and so forth, that all lie within our confidence region. And our confidence region is the open interval a minus epsilon, a plus epsilon, which means each term that's each of these terms themselves lie within an epsilon distance from the limit a. Now recall from this, from neighborhoods, this is the same thing as the absolute value of an minus a less than epsilon. That's what we mean in the definition. So right here, this is basically meaning our ANs lie in the interval a minus epsilon, a plus epsilon, and each AN is in that interval. All right, and that's like I called that the confidence region. Okay, so again, formalizing the language. A sequence an converges to some number a as n goes to infinity means if and only if for all epsilon greater than 0, I can find a capital N that's in the natural numbers so that for all little n bigger than capital N, we have that the distance from an minus a is less than epsilon. So in other words, an converges to the limit a if and only if for all, you could say confidence values epsilon greater than 0, I can find a value for the index such that for all indices beyond this particular value of the index, we have the nth terms within an epsilon distance of a. All right, that's what that translates into. And graphically, that's sort of what it represents here. And that's what I said. All of these terms that I circled are the terms that have index n greater than n, capital N, and these are all terms that lie within our confidence region, a minus epsilon, a plus epsilon, which is the same as the absolute value of an minus a less than epsilon. And each of these terms lies in that confidence region, which means each of these terms are within a distance of epsilon from the limit a. And so the question, or what we're trying to do in these proofs that we'll do in a second, is we want to find this capital N so that all the little n's bigger than n are in our confidence region. So we want to find this, I think of this as the cutoff point. The cutoff value. Okay, so for our example where we had the sequence 1 over n, and I claim that it converges to 0, so we're going to prove this claim. And again, 1 over n, right, that's 1, 1/2, 1/3, 1/4, dot, dot, dot. we're going to show that that converges to 0 using the definition. Now for the strategy, the Archimedean principle says that for any real number greater than 0, there exists a natural number n such that n is bigger than 1 over epsilon. And we can take the reciprocal of both sides, and that gives us 1 over n is less than epsilon. So we need to find the cutoff point capital N so that for all indices little n bigger than capital N, we have that the term 1 over capital N is less than epsilon. All right, that's sort of the strategy here, and I'm invoking the Archimedean principle. Okay, so here's the proof. So first we have to say given epsilon greater than 0, right? So there's got to be, start out with saying for all epsilon greater than 0. That's what we start the proof with. So given epsilon greater than 0, and I put in parentheses what we're trying to show. We want to show that there exists some capital N in the natural numbers, so that for all little n bigger than capital N, we have the absolute value of an minus a less than epsilon. Keep in mind our terms, or an's, have the structure 1 over n. And we're trying to prove that it converges to 0, and so our a value is 0, so we want absolute value of 1 over n minus 0 less than epsilon is what we want. So by Archimedean principle, there exists a natural number, capital N, such where capital N is bigger than 1 over epsilon. So taking the reciprocal, then we have 1 over capital N is less than epsilon. So that means for all little n bigger than capital N, which we know capital N is bigger than 1 over epsilon, so we have n bigger than capital N, bigger than 1 over epsilon, reversing those inequalities, taking the reciprocals, we get 1 over little n is less than 1 over capital N, which is less than epsilon. All right, and that's the value, cutoff value we need for capital N. So our cutoff value for capital N is the n bigger than 1 over epsilon, which we know is guaranteed by the Archimedean principle. All right, so for little n bigger than capital N, we have the absolute value of an minus 0, because our limit that we're talking about is 0, equals, and our terms have the structure 1 over n, so it's 1 over n minus 0. And that's equal to 1 over n, so we have that as the absolute value of 1 over n. And the absolute value of 1 over n is less than or equal to 1 over, and then this is little n. But we know that 1 over little n is less than 1 over capital N. And we also know 1 over capital N is less than epsilon. And so that completes the proof. So we've shown, so the proof is done at this point, but we've shown for all epsilon greater than 0, there exists a capital N, so that for all little n bigger than n, we have our sequence is 1 over n, so 1 over n minus our limit value in question is 0, it's less than epsilon. All right, that's what we've shown. And again, the values n's are dealing with the index for the terms in which the terms themselves are within epsilon distance of the limit, 0. And we had to use the Archimedean principle to find this capital N. All right, so notice our choice for capital N depends on epsilon. I put depends in quotes. So I like to think of it as a game and call it the NE game. And basically, you give me an epsilon, I got to find the corresponding capital N that will make the proof work. All right, that's the idea for these. So you're given an epsilon, then you got to find the N that makes that makes it work for the proof. Okay, so that's that example. So I'm going to label such ins as, so to employ that idea that it sort of depends on our epsilon, that it's going to be capital N parentheses E, or capital N parentheses epsilon. And that'll be for the rest of this video. So for the limit definition, I'm going to say AN converges to A if and only if for all epsilon greater than 0, there exists this capital N parentheses epsilon, that's a natural number, so that for all little n bigger than this capital N, we have the distance of AN minus A is less than epsilon. All right, so that was the example with 1 over n that we've shown converges to 0. Now this example where it alternates 2, 0, 2, 0, we're going to try to show that it diverges. Well, we know what it means to converge. All right, so this is the definition for converges. So for diverges, we take the negation of that statement. And the negation would be, so AN does not converge to A, if and only if, and you switch these quantifiers. So the for all epsilon becomes there exists an epsilon. The exists an n becomes for all n that are in the natural numbers, and then you switch the quantifier for all little n bigger than n. That's going to be there exists in little n bigger than n, where the distance, and you flip the inequality, so you switch it from less than to greater than or equal to. So where the distance of AN minus A is greater than or equal to epsilon. So that is the negation of the statement. And so we're going to utilize this negation. And so we got to basically, since there exists an epsilon, I just need to find that epsilon. And so let's say epsilon is 1. And we might guess that, well, since the terms of the sequence are either 2 or 0, then the limit might be one of those values. So let's consider the case when the limit is 0. Well, since we have for the odd numbered terms, odd indices, we have the value 2, then when we do the absolute value of AN minus A, which is going to be the absolute value of AN minus 0, because we're considering A being 0, our nth term, if we're considering only the odd terms for the nth term, that's 2 minus 0, which is equal to 2. And now 2 is greater than 1, which is what we're using for epsilon. So I've produced a value where it falls into this sort of criterion. Now, if we have an even index and we try to guess that the limit is 2 this time, but for all the even index terms, we know the nth term is 0. So we have the absolute value of AN minus A is equal to, and in this time we're considering 2 as a limit point. So we're doing A is 2, and then our nth terms are 0 since we're dealing with the even indices. So it'd be 0 minus 2, which is also going to be the absolute value that is still 2, which is greater than our value that we chose for epsilon 1. So that follows the negation statement. All right, so now that's the strategy. Now the actual proof. It's very similar to what I wrote here, just formalizing it. All right, so we will show that the sequence 2, 0, 2, 0, ... does not converge. Now, if it were to converge, a reasonable guess might be 0 or 2. So the case 1, consider 0 as our limit point. We're going to pick epsilon equal to 1. Then for any capital N, that's a natural number, consider little n equal to 2 times that capital N plus 1. So that means we're dealing with odd numbers for n. So odd value for the index little n. All right, so for little n bigger than capital N, where n is odd, hence we have the absolute value of an minus 0, because 0 is the value we're considering as our limit point. We know for the odd terms, odd index terms, it's 2. So you'd have the absolute value of 2 minus 0, which is equal to 2. And we know 2 is greater than 1, and 1 is our value we chose for epsilon. So yeah, we produced, so this case means we've shown there exists an epsilon greater than 0, namely epsilon is 1, so that for all capital N in the natural numbers, there exists little n bigger than capital N, and this little n we were using to be the odd values, and that was going to be n equal to 2 n plus 1. So there exists that particular n that's bigger than capital N, such that an minus a is greater than or equal to epsilon. So we've shown that, and in our case, we had for the odd index, it was going to be 2 minus our limit point that we're considering is 0, so 2 minus 0, which is greater than or equal to 1. All right, because our 1 is the epsilon value we've chose. All right, now the second case, let's consider 2 as a limit point. Now, if 2 is a limit point, again, we're going to still pick epsilon to be 1. Then for any capital N, that's a natural number, consider little n equal to 2 times capital N. So that means little n is an even number. So we have for little n bigger than capital N, where little n is even, hence the absolute value of this time our limit point is 2. So we're using a equals 2 for this case. So it'd be the absolute value of the nth term minus 2 equal to, since we're dealing with the even indices, those are going to be 0 for the terms. So it'd be the absolute value of 0 minus 2. Absolute value of 0 minus 2 is 2. And 2 is greater than 1, which is equal to the epsilon. All right, so in either case, we've shown that it does not converge, right? So, but what did we really prove here? All we've really shown is that our sequence 2, 0, 2, 0 doesn't converge to 0, and it doesn't converge to 2. But these are specific values that we chose for the limit points. We didn't show, though, is that it doesn't converge for any value a. So how do we show that it does not converge for any value a? I hope that makes sense. So this particular example, we've only shown so far that if 2 and 0 were limit points, it's not going to converge to those 2 limit points. And the way that we've shown that was using the negation of what it means to be convergence. So we haven't shown, though, is what happens if a is arbitrary, just an arbitrary real number. So that's what we actually need to show. All right, so how are we going to show this? So for the strategy, I'm going to assume, for sake of contradiction, that it does converge. So let's say it converges some value a. Okay, so we're going to assume to the contrary that it does converge to some value a. Well, what does that mean? This means For all epsilon greater than 0, there exists a capital N in the natural numbers. And I'm just going to use, I'll use it with the epsilon, capital N parentheses epsilon. So that for all little n bigger than this capital N, we have the different absolute value of the difference, an minus a is less than epsilon. All right, so we have that assumption. Now, if we're going to do a contradiction proof, then we need to find something that's going to contradict this. So if we can produce an epsilon value, so it just needs to be one epsilon value because this is supposed to happen for all epsilon. So as long as we can produce a single epsilon value, if we can produce an epsilon greater than 0, for which this isn't true, then we get a contradiction. All right, and I'm just going to pick a value for epsilon and just see what happens. So let's just say we had 1/2. Let's just pick all right, let's say epsilon is 1/2. Now we know for our odd indices, our odd terms, we have an 0. Our even terms, our odd terms are 2, even terms are 0. All right, so let's do the case. Well, that means an absolute value of an minus a. That's going to be equal to the absolute value of 2 minus a. And then for this one, that's going to be the absolute value. So 0 minus a. All right, and that's just the absolute value of negative a. Now we know for absolute values that the absolute value of negative a, that's also equivalent to the absolute value of a. So here's a trick that we're going to do. So this trick, you're going to add 0 in the following fashion. So 2 is the same thing as 2 plus 0, and I can write 0 as plus a minus a. All right, then I can, by associate, so 0 I'm representing as plus a minus a. And so if I have the absolute value of 2, that's equal to the absolute value of 2 plus a minus a. And we can rearrange this so that we have the absolute value of 2 minus a plus a. Now, by triangle inequality, this is less than or equal to 2 minus a plus the absolute value of a. So this is the triangle inequality. Now we're letting epsilon be a half. So each of these, the 2 minus a, if it was an odd term case, then the absolute value of 2 minus a has to be less than 1/2. If it was an even term case, then we we had 0, absolute value of 0 minus a, which is eventually equal to absolute value of a. That also has to be less than a half. All right, so that's, again, we're assuming it converges to value a, so it's got to work for every epsilon. So let's make our lives easier and just pick a specific value for epsilon, and I just chose it to be 1/2. So that means for the odd terms, I get the distance from 2 to a, or 2 minus a, that's going to be less than 1/2. And then the difference, absolute value, the difference from 0 minus a has to also be less than 1/2. Now, if that's true, then this 2 minus a, that's less than a half. So we have that's less than a half. Absolute value of a is less than a half, so that's plus a half. So we have 1/2 plus 1/2. What's 1/2 plus a half? That's equal to 1. But notice we started out with 2, absolute value of 2. So what we're saying is 2 is equal to the absolute value of 2, which we wrote this out as 2 minus a plus a by adding 0. Writing the triangle inequality, that's absolute value of 2 minus a plus a. And then these two things, when you add them together, they're less than a half plus a half. And 1/2 plus a half is 1. So essentially we're saying 2 is less than 1, which doesn't make any sense, right? So that's a contradiction. All right, so that's how we're going to do the proof, and we're going to use the triangle inequality. All right, and the trick was to add 0, where it was plus a minus a, and make use of what we know for the odd terms and then the even terms. All right, so I kind of pretty much did the proof, but let's just make it a little bit more formal. Proof. So we're doing a contradiction proof. So assume to the contrary. So we want to show that it doesn't converge, right? So we're going to assume to the contrary that it does converge. And our sequence is 2, 0, 2, 0. All right, let's assume to the contrary that that converges. And let's say we'll call this value that it converges to some number a. Some a in the real numbers. This means when for all epsilon greater than 0, there exists some capital N such that for all little n bigger than capital N, we have absolute value of a in the nth term minus our particular value limit a is less than epsilon. All right, so since that's what we have, it's got to work for every epsilon. Let's pick epsilon equal to a half. Note that for the odd index terms, so note that for so we want it to be odd indices. So let's for all indices for odd indices n bigger than capital N. In other words, we're going to set n equal capital N plus 1. We have that the absolute value of an minus a is equal to our odd terms are 2, right? So it would be 2 minus a. Well, a is just our limit that we're interested in, so we just say it's 2 minus a. And that's less than epsilon. So that's less than 1/2. All right, because that's our epsilon value that we chose. All right, then for the even indices, n bigger than capital N, i.e. little n is equal to 2 times capital N. So that's just the format for even, so 2 times an integer. So then we have that the absolute value of an minus a, and again, our odd terms are 0, even terms are 0, or sorry, odd terms are 2, even terms are 0, so that's going to be 0 minus a. Well, the 0 minus a, that's equal to negative a, absolute value of negative a, which that itself is equal to the absolute value of a. And then that's going to be less than 1/2, since that's less than epsilon, because we're assuming that it already converges. Okay, so we have those assumptions, so this is where we're going to get our contradiction. But 2 equals the absolute value of 2, which that equals the absolute value of 2 minus a plus a. And then that, by triangle inequality, is less than or equal to the absolute value of 2 minus a plus the absolute value of a. So that should be a triangle inequality. But since, based on our assumptions, so we have that 2 minus a, absolute value that's less than 1/2. This is less than 1/2. Absolute value of a is less than 1/2, so it would be less than 1/2 plus 1/2. So 1/2 plus 1/2, that's equal to 1. But this says 2 is less than 1. That's just contradiction. All right, and then we're done. So therefore, our sequence does not converge to any number a. Okay, so that completes the proof. All right, so the reason I had to do that was because in the ones we did before, I specifically chose two values for possible limits. All right, we did 0 as a limit point, showed that that gave us the contrapositive statement that we were showing for it to not converge, and then same thing when I chose, so I chose 0 and 2 as limit points. Those are specific values for limit points, but we needed to show how does it not converge for any value a, and that's what this was, this proof. And then again, I usually do in yellow what's my thought process or the strategy behind the proof, and it relied on this trick where you add 0, and throughout the course you'll see me do that multiple times where we add 0 in a clever way so that we can make use of the knowledge that we know in the question. And that's what we did here. And then that way we had a statement that's a contradiction, 2 less than 1. All right, so that's it for this video. This video is meant to give you sort of a glimpse into sequences, get our feet wet. We're going to go into more stuff and sequences in the next video and prove some theorems.